So welcome to everyone to the new Colloquium of GSSI. It's our great pleasure to have Daniel Ueltschi from Warwick University here in L'Aquila. Daniel is in this week's giving a nice class of introduction to our students on quantum spin system. Actually, Daniel is recognized, well-known expert both in classical and quantum statistical mechanics, and in particular on the emergence of universal behaviors or phase transition in classical and quantum interacting system. Today, he will give a talk on loop models and universal distribution of the loop lengths. Thanks a lot, Daniel, for accepting our invitation to be here at GSSI.
Well, many thanks, Serena, and many thanks to the organizers for this invitation to this wonderful place. My first time in L'Aquila, I'm really impressed. I still have not understood why it's called the Gran Sasso Institute, since one cannot see the Gran Sasso from here, as far as I can tell. But it's, no, I mean, I'm just kidding. It's really a beautiful place, and with friendly people, so it's really a pleasure to be here. And yes, I'd like to discuss loop models. I think I have too much material anyway, so do ask questions. I'll see what I can cover. Hopefully, everybody can take something out of this talk. Questions are really welcome. So if I have time, I would like to discuss some loop representations for quantum spin systems, and then explain some numerical results, some conjectures. Lots of things can be guessed, can be conjectured, in fact, and only partial results can be actually obtained. So there are lots of future work which is necessary. Then I will explain, I mean, there will be this conjecture about certain joint distribution for the lengths of loops as behavior, I mean, the heuristics behind this behavior. I will explain some results from mean-field systems. If I have time, discuss a little bit the ideal Bose-gas and something about classical spin systems, which are results going in the direction of this conjecture. So, the first loop representations for quantum spin systems. So quantum spins are really quantum systems, and generally they cannot always be described by probabilistic tools, but some of them can. And in some cases, one can, introduce a probability measure on a nice space of loops and get something out of it. So just to recall the setting about quantum spins, if you see it for the first time, I think it will be a bit too fast, but we look at a finite set of sites or finite graphs also. The Hilbert space for this finite number of spins is the linear span of classical configurations. So for those who are familiar with the Ising model, we have like Ising configurations, and we turn this into a Hilbert space by declaring all those configurations to be basis elements, and the Hilbert space consists of a linear span of all those configurations. We have the spin operators. One way to describe, to define them is by introducing the commutation relations that they satisfy. Like the commutator between S1 and S2 is IS3, and between S2 and S3 is IS1, and so on. Another way, how they act on the basis vectors. For instance, the S3 is diagonal in this basis, and we have this property over here. Then this is the Hamiltonian of the system. So that's the operator which represents the energy of the system, and it's a sum of all the nearest neighbors of those spin operators here. There is this parameter delta. Depending on the values, we recognize important models. When delta equals 1, that's the so-called Heisenberg, quantum Heisenberg model for this so-called spin 1/2 particle, spins. For when delta is strictly between -1 and 1, that's the XXZ model, sometimes called XXZ because you have, this 1 sometimes is written as X, and 2 Y, 3 is Z. So then this would be like the X interactions, the Y interaction, and the Z interactions, to say that those two interactions strengths are the same, and this one is different. One writes this as X, X, Z. If delta equals 0, you don't have this term. That's one way to write the XY model. Delta equals -1 turns out to be important in many respects. It's a unitary equivalent to the Heisenberg anti-ferromagnet, which is the same model, but with a different sign here. So this is the class of models that we are looking at. And this represents the energy of a system of quantum spins interacting between nearest neighbors. These are so-called ferromagnetic interactions. The energy is a bit lower when the spins are in the same direction. That's the intuition. So this is going to introduce correlations between the spins in such a way to encourage the spins to point in the same direction. So the question in statistical mechanics is whether these nearest neighbor interactions are strong enough to bring an overall magnetized phase. So anyway, once you have the Hilbert space, sorry, the Hamiltonian, you can define Gibbs states, which represents the equilibrium property, equilibrium behavior of the system. The expectation of a given operator is given by the trace and of the operator here with the exponential minus beta h. And one divides by the partition function, which is the trace of exponential minus beta h. So the expectation of the identity operator as it should. So I'm going to explain the representation due to Balintort for this quantum Heisenberg model. So suppose you have a finite graph. So lambda is the set of vertices, E is the set of edges or nearest neighbors. And so we have interactions between spins and nearest neighbors. And the picture is like that. So I'm going to introduce a kind of a completely different model, which is really a probabilistic model. And then I will state the equivalence with quantum spins that we had before. So here you have the graph. So it's a linear graph because I need an extra dimension to explain the representation. And for each edge, we look at, we introduce some interval from 0. Here that would be 0. Also, I change the 0 here. And beta over here, beta being the inverse temperature of the system. And now, on this interval, you run a Poisson point process denoting, for instance, you can have an event occurring at this time and another one at this time here. For some reason, we denote the occurrence of an event by this cross, by these crosses. So this is on top of this edge. You have the interval. And you have those events possibly occurring. For the next edge, you only, again, look at this interval. Again, you run the Poisson point process independent of the previous one. And perhaps we have something here. And you continue. For each edge, you have this time interval on top of it. And you have independent Poisson point processes. Once we have a realization of these Poisson point processes, so a set of these crosses here, we define loops. And for the loops, we start anywhere and we move up. Oh, that's a big size. How do I change the size of the? Okay, never mind. Oh, but it's really too big. So let me do this thing. Okay. So we move up, and then when we reach the cross, we follow it, continue up, and then we get some kind of trajectory like that. When we reach the top of the interval over there, we continue from below using periodic boundary conditions in the vertical direction, and we continue until we close this trajectory. So we reach here, and then we do that. And eventually, we are going to close all this thing, not yet. And here, now we are coming back to the point. And so this represents one loop for this realization of a system. We can start somewhere else here, and we get another loop. So this one here. And we can also look at another loop over here. And now we have identified all the loops of this configuration. Why are loops important? For two reasons. One is that we need to modify these probability distributions on these crosses according to this weight over here, which is 2 to the number of loops. So we tilt a little bit this measure on crosses towards having a bit more loops. And the second reason to get the loops is that we can not, I mean, now we have natural correlations between different sites. We can ask whether two sites belong to the same loop or not. And as it turns out, this will represent spin correlations. So is the model kind of clear? I mean, we start with a graph here. We look at each edge. We have Poisson for each edges, for each edge, sorry. And so for given realizations, we have this notion of loops. And the corresponding measure is this one over here. So this represents the collection of Poisson, independent Poisson point processes. But then we have this weight over here, which brings a dependence on all those crosses. And actually, I'm also going to consider generalization of this, where the Poisson point process, in fact, has two events. We have the crosses and the double bars. So when you decide to put something with probability little u, you get a cross. With probability 1 minus u, you put a double bar. And then you define loops in the same way, except that when you go up, a double bar means that you change direction. And you follow this prescription. Here you continue over here until you close the loop. So here we have, I mean, there is the loop in red and the other loop in blue. And here is just a picture to show you, but also if we have a graph which is not linear, we can have a picture. If the graph was not planar, it would be hard to depict, but it's easy to, I mean, it's clearly well defined. So in any case, this is in general, the measure we consider 1 over a suitable partition functions, so that we have a probability measure. This theta, which is a positive parameter, to the number of loops. And otherwise, this is this collection of Poisson point processes. And the relevant theta is, I mean, mainly it's theta equals 2 for these quantum spin systems, but also theta equals 3, 4, and so on corresponds also to interesting models. And here is the equivalence between the quantum spins and the loops. So this is the Hamiltonian that we had before. Okay, it turns out one should put a factor 2 here, put a little bit of a constant here. It does not change anything about for the properties. And also the asymmetry parameter should be put in the middle. But otherwise, you really have this, I mean, it's like X, Y, X model. And this parameter, I mean, this thing has the parameter U. So for U equals 1, this is 1, and this is the Heisenberg model. But otherwise, we can consider a U which is between 0 and 1. And that's the equivalence. The quantum partition function, or that's the normalization for the quantum system, is actually the normalization for the loops. And that's not a trivial thing, because this is a function of this beta, for instance. This also depends on beta in the sense that the interval for the Poisson point process has length beta. And what is really nice in this representation is that the 2-point function, the spin correlations, I mean, which is the same in the direction 1 and 3, because the system has similar interactions here, is given by loop correlations. So this is the correlation, I mean, the probability that the site 0 is connected to the site with the site X at the time 0. And that's the model with the loops. And then we can also look at this kind of correlations. So we should expect something different because we have different interactions here. And it turns out that this quantum, I mean, the spin-spin correlation is given by the probability that 0 and X belong to the same loop. But in addition, things go in the same direction. So if you start going up over here, when you reach X, you should also be going up, minus a probability that when you start going up, you go down. And you can check that, I mean, in the isotropic case, so u equals 1, you have only crosses. If you start moving up, you keep moving up. So this has the full probability. So then this thing is equal to the probability of being connected, which is equal to, I mean, to this and this. So if you have only crosses, this correlation function must be the same as this, and indeed it is. So I have a few slides of how to derive these representations, but I'm going to skip this. But let me discuss what is expected for this system. So here is a very simple calculation. You look at the expectation with these loop models of the length of a loop at, I mean, which contains the origin. So in your graph, you have a site which is designated as the origin, so denoted as 0, and L0 is the length of the loop containing this site. The length of the loop means the number of sites at time 0 that the loop meets. So then expectation of this, I mean, this L0 can be defined as the sum of all sites and the indicator that the site X is connected to 0. Then expectation of sum is sum of expectations. So you have the sum of the expectation of the indicator. You all remember that the expectation of an indicator is a probability. So you have a sum of the probabilities that X is connected to 0, and which is also this spin correlation function. So what we get is, I mean, for those who are familiar to statistical mechanics, this is I mean, an operator which is related to long-range order. So you sum over all X. I mean, imagine that you have a very large system, and you look at this sum of correlations between a given site and very far away. So the question is whether when X is very far from 0, do we get something small, or do we still get something large? So if we get something large, then this sum is of order the volume. If this two-point function decays fast, then this sum should be of order 1, even for volumes which are huge. So when beta is small, I mean, in this picture, sorry, beta small means that this interval is very small. So you run a Poisson point process of intensity 1. You have almost no time to put anything. So typically you have an empty configurations with nothing. The loops are just straight lines, and they don't reach very far. So this is a situation where you have plenty of loops not going far, and you expect the loops to be small. So L0, the loop containing 0, should be microscopic when beta is small. But in general, it's harder to say. In dimension 1, so when you have the graph is this linear graph with interactions between nearest neighbors, nothing interesting happens. I mean, one could introduce longer range interactions, and this becomes a very interesting problem. But for nearest neighbors, nothing interesting for finite beta. For dimension 2, so when the graph is like a finite, I mean, like a box in Z2, but a huge box, we expect tightness. And this is something which is just not very clear about what to expect. But I would argue that the limiting probability measure is tight in the sense that if you sum over all possible lengths of loops, then you still get 1. Or in other words, if you look at the probability that the loop is larger than k, so in a finite domain, it is going to be 0 if k is larger than the volume of the system. I mean, the number of sites. But you first take the infinite volume limit. I mean, this is a box of size L, I mean, L times L. So you first take the infinite volume limit, and then you take k to infinity. So what is expected is that this still is 0. So I mean, when you look at the distributions of possible lengths, with probability 1, you have finite lengths. But at the same, yes? Capital L is the length of the system here. So I should have explained it, but I imagine that we are in a box of size L. I mean, this would be inside Z2. So these are the sites. And it means that the loop is necessarily smaller than the, I mean, the length of the loop is the number of sites it is. So it is touching. So it cannot be more than L square. But if you take L to infinity first, this could a priori be arbitrarily large. So this says that no, one should not expect it. At the same time, and also if beta is small, it's not hard to check, but you have exponential decay for these kind of things with K. So for instance, if you look at the expected length of a given loop, if you have, I mean, the property measure with exponential tail, then that's finite, obviously. But what could happen over here is that for beta large enough, so one would expect a beta, I mean, if beta is small, this thing is always finite. And for beta large, it could be infinite. For u equals 0, 1, as it turns out, this corresponds to the Heisenberg model. And this is something which is still quite an open conjecture. One would expect in 2 dimensions to have exponential decay of correlations for all beta. But it's believed by most physicists, but it's not completely uniformly trusted. So it's one of these open things. Heisenberg model in 2 dimensions. But if you're in the XY regime, one expects a cosine Staurless where the correlation function goes from exponential to polar. And then we could have some moments becoming more complicated. So this is still not completely clear about what to get. But just to point out that interesting things may happen already in 2 dimensions. In dimensions 3 and higher, one expects the following, but if you look at the expected length of a loop, but you divide by the volume of the system, then if beta is large enough, this should be bounded away from 0 uniformly in the size of the system. And for those who attended my lecture this morning, that's precisely what I explained, because I did the proof, I mean, very quickly, for a class of system which contains some of these loop models. So I mean, a very long list of interesting results. There are results on trees, results on the complete graph. I mean, a very important result by Odette Schramm, who really understood first this Poisson-Dirichlet structure, which I'm going to explain shortly, on the complete graph. And this was done for u equals 1. And recently there was this result by Jakob Björnberg, who is here with collaborators, also with a model with reversal, where they can prove Poisson-Dirichlet not of 1, but of 1/2. There is a change over there. And recently, nice results on random regular graphs due to Pudovigne, and a very impressive result by Elboim and Sly on Z5. So this is really this model of loops on a genuine model with spatial structure, I mean, on Z5, and they can prove the occurrence of long loops. So if beta is large enough, at some point the loops become, I mean, they are on Z5, so the loops go to infinity. And of course, I would like the results. This should happen in Z3, but okay, for many years, it was not clear at all how to get anywhere to ZD. So Z5 is an impressive result. Some results also for the random loop models. When we have this theta, so this is this crosses, but this time everything is weighted by the theta. And I mean, normally it's more complicated, but in some cases it's a bit simpler because there is quantum spins. And one result is that, I mean, due to Komatasaki for the quantum spin system, is that this probability in 2 dimensions decays like a power law. I mean, that's also something I explained yesterday, actually, in my class here. The proof for the quantum spins, which can be understood as a result for those loop models as well. But this is a result on the loop models only for those. If the result is true for when you have these weights 2 to the number of loops, it's also true when we have 3 to the number of loops. It's kind of clear that there should be some kind of interpolation. There should be some kind of inequality. This probability should be probably monotone in theta. So one would expect that if it's true for 2 and 3, it should be also true in between. But I have no idea how to get a claim like that. And for dimension 3 and higher, okay, so this is, there is a restriction here, which corresponds to having these J2 interactions less than 0, I mean, for those who were in my class this morning. Then we can prove the existence of macroscopic loops, provided beta is large enough, and dimensions 3 and higher. So this goes back to the work of Fröhlich, Simon, Spencer, reflection positivity for classical spin systems, and the work of Dyson, Lip, Simon, which I reviewed this morning. But so this is a nice result because it shows that in dimensions 3 and higher, one should expect, I mean, first, the occurrence of long loops and how long they are. So if you're in a box of size L, one should expect them to be like L to the D. So the expectation of L0 divided by LD is not 0. I mean, C is positive. So now what I'd like to discuss is the joint distributions of the lengths of loops. We have quite a few loops in the system, and so omega represents realizations of its crosses and double bars. Given realizations, we can look at all the loops we have. So we have the number of loops, it depends on the configuration and realization. So this is this capital K. And L1 is the length of the largest. L2 is the length of the second largest, and so on. So now let's look at this random vector here. We take the largest length divided by the volume, second largest, and so on. So what we get is a vector of positive numbers. Those numbers decrease by construction. And in addition, they add up to 1. Because when you sum over all lengths, remember that the length of a loop is the number of times it crosses, I mean, the number of sides at times 0. So when you add all possible, I mean, the sides of all possible loops, you have counted exactly all the sides of the system. So the sum of all those lengths obviously should be like the volume. So since we divide by the volume, this is always a partition of interval 0, 1. And what one expects is that with positive probability, a given site may belong to a small loop, because you could imagine a given site not having any cross or double bar, so just the length of a loop is 1. So if you have a huge system, you look at the smallest over there, there should be a bunch of 1. So you have tiny things. So that's why I showed here tiny ticks here. So this, I mean, if we take something like that, so this length over here, the length of the smallest would be like 1 over the volume. I mean, exactly 1 over the volume. So if the volume is huge, these are tiny things. So we expect a lot of tiny things, and perhaps at some point we have lengths like 2 over volume, but still something getting to 0. On the other hand, what we know is that if we take the expectation of a given one, I mean, the loop containing the origin divided by the volume, it is positive with, I mean, the expectation is strictly positive. So one would expect the largest to be of macroscopic size. So we expect the largest to be like that, second largest perhaps like that. And yeah, I mean, so we have this property. So what do we get? So these are the realizations of numerical simulations. That's for this model with the crosses. This is the same parameter beta. It's just 4 different realizations. So in the first one, I mean, you see that the length of this thing is this width over here. This thing is this one here. And then another one. And we get some kind of an accumulation point at this point. And then from here, all the other loops are so small, but it looks like a thick line. So this is one realization. Then you can do another random realization with the same parameters. And what you see is that in the second one, the largest loop is a bit larger than this one. Second largest is smaller than this one here. And you still have an accumulation point. The accumulation point is at exactly the same value. And then you get, again, the tiny things. And you have 2 more realizations. What we see is that this accumulation point has typical behavior. I mean, if you look at the length of the largest loop, this varies from one realization to the other. But something which is typical is this accumulation point. So then we expect, I mean, here is the conjecture, which, I mean, it was a bit surprising to see this happening in ZD. So that's somehow what the Schramm observed in the complete graph, but this happens in Z3, I mean, ZD with D larger equals to 3. So what is expected is that we should get an accumulation point, which can be understood like that. So you sum over the K largest. So basically, you cut things at some value over here. You take the system size going to infinity, and then you keep, first the system size going to infinity. Then you take the limit K goes to infinity so that you reach all the points over here. And then this is one way to identify this accumulation point. So you expect this to take typical values. For almost all realizations, I mean, if the system size is large enough, you should be very close to some fixed value. One has to do it this way because if you sum over, if you take K to infinity first, then you are summing over all possible lengths, and this is 1 by construction. So it's very important to first kind of get rid of the tiny things, but then we take K to infinity so that we take everything up to the accumulation point. Yes?
1 second.
You say again what is K?
This little K?
Yes.
Well, so we fix a K, and then we take it to infinity afterwards. So this depends on K, little K, and the idea is that what we expect for very large systems is that we have for sure, but more and more when the system size goes to infinity. And so we want to identify the accumulation point, but so we up to K equals 1000, and then we take the infinite volume system, the infinite volume limit. Yeah. Thanks. And then, so this is the first part, but this there is almost surely this accumulation point. And the second part is that if you look at this part of the random partition, then this converges to a so-called Poisson-Dirichlet distribution. So it's a measure on random partitions, which I'm going to explain. And so yes, that's the claim that there is this important probability measure on partitions, which turns out to be present here. And it's quite remarkable because it doesn't depend too much on the structure of a lattice. It's the same Poisson-Dirichlet no matter the dimension is, large or equals to 3. If you change the lattice by introducing like next nearest neighbor interactions or things like that, well, you would be changing this M star, but you would not be changing this Poisson-Dirichlet. So here there is one paper. I'm not part of this et al. So there is a group of people completely independent of myself who has also checked in some different loop models that this happens. So, and this is we did it for lattice permutations, which is yet another model involving loops in dimensions 3. Here, these are exactly for this models I explained, and this is also in when we have this theta equals 3. So something I'd like to point out because okay, it's a recent result and just a bit I found a bit curious. So this is the loop models for theta equals 3. And here we vary parameter beta. And the question is I mean, the question here was more like statistical mechanics. We would like to know when we vary beta. So we go from the phase with long loops to the one without loops. At critical beta, when the change happens, do we have coexistence between the ordered low temperature phases and the disordered high temperature phase, or are we going smoothly from one to another? It's something which is not obvious. I mean, for the Ising model, it was proved only recently that the transition was smooth in dimension 3 by Limnit-Copin, Eisenman, and Sidora-Vicious. So it's Fields medal level. And in dimension, I mean, for things like Ising models, but I mean, called random cluster models, it's known that we have also coexistence. I mean, we have coexistence in some cases. And so here we have these numerical simulations. And what happens is that, so Niels Ueltschi was really the one who was doing these simulations. He did simulations, for instance, when the length is 48. So it's quite a large system. It's 48 aside in 3 dimensions. So 48 times 48 times 48. And we look at the expectation of a certain observable. And then we see these kind of things. So the fact that you get things a bit like a Gaussian suggests that you have a single phase. So you have like a typical value for this phase, and there is some fluctuations. So when you make many experiments, you get this. But so the fact that there is a single peak suggests that there is a single phase. But if you go to to even higher lengths, then you start seeing something funny occurring. And for very large lengths, you see, because this time, I mean, if you take a typical realization of a system, since you have coexistence, then you would pick up which coexistence phase you have. So it can be sometimes ordered, sometimes disordered. And then you will be averaging. I mean, this would be the contribution of one of these things, let's say the ordered, and this could be the expectations of the disordered. And then since you have the coexistence of the two, you get the superimpositions of these two peaks. But this is what the physicists call weak first order phase transition, because they are hard to find, basically. So you need system size which are quite large. So I mean, if you do a system size of like 10 to all the way to, let's say, 50, then you would just not see it, and you would conclude that it's actually a smooth phase transition, continuous phase transition. So it's only when you take large systems, I mean, basically around this 70, that you start seeing that something may occur. So, all right, so I just find, I was keen to understand this difficulty for the numerations to understand what was happening. So what I'd like to discuss now is this universal behavior of Poisson-Dirichlet. And the Poisson-Dirichlet distribution is something which was introduced explicitly by Kingman. It became very important in mathematical biology, and but it also shows up in statistical mechanics and in different topics. It's easy to check that. I mean, for those people who like sports, you can look at the. I mean, like when the records are performed, and look at the times when the records are performed, and then you can look at all those times. I mean, when they are performed, all these intervals of times, divide by the total amount of time, and then you get a random partition. It turns out that this is Poisson-Dirichlet distributed. I mean, or it should be if if actual realization really follows independent events. Anyway, let me describe it. So it's easier to describe a related random partition called measure on random partitions called the GM distribution. And this is a so-called residual allocation measure, which can be done by stick breaking. So here you have the interval 0 to 1 and the picture. So what, right. So we choose lambda 1 uniformly in 0, 1. So we take this number over here, and lambda 1 is this width over here. Now, the next step is to look at this interval here, and again, choose the number over there uniformly at random. So for instance, that could be lambda 2. We take this one, and so we define lambda 2 like that. With probability 1, there is still a remaining positive interval, so we continue this. And then, I mean, the remaining interval becomes smaller and smaller. So you're going to add numbers which are smaller and smaller. So here you get a sequence of numbers. They are positive, and with probability 1, they all add up to 1. And if you rearrange these numbers in decreasing order, you get Poisson-Dirichlet. I mean, as you see, lambda 2 happens to be smaller than lambda 3. So you have to take all those numbers, get from the largest to the smallest. You get a random partition, and this is Poisson-Dirichlet of parameter 1. And this is this Poisson-Dirichlet is a one parameter family of distributions. You can do the same constructions. Instead of using the uniform distribution on 0, 1, you can actually take any distribution on 0, 1. It turns out that the correct, I mean, the relevant distribution is to take a beta random variable, so that you have this property over here. And so you pick up lambda 1 with this distribution. This thing, which is smaller than, I mean, it's a smaller interval. So imagine that you resize it to 0, 1, use the same distributions, and then size it back. Then it gets the lambda 2. And then with what remains, you do the same thing. And then again, you order the numbers from the largest to the smallest, and you get Poisson-Dirichlet of parameter theta. Correct.
Yes.
What I do, I correct.
So you said instead of uniform, we can take any distribution.
Yes.
And so, then you said the correct is the better.
Relevant. I mean, it turns out that these Poisson-Dirichlet distributions have a special property. They are the invariant measures of the split merge process. And that's what is really important for us. But it's true that for this residual allocation construction or stick breaking, you can take an arbitrary measure on 0, 1. But I mean, those which are called Poisson-Dirichlet are this family when we take a beta random variable on 0, 1 as the driving measure. And the heuristics is that, I mean, we have this loop model with this data to the number of loops, which gives some correlations between everything. And so we can look at this probability measure here. And the idea is to view this probability measure as the invariant measure of the stochastic process. So we run some kind of Monte Carlo simulations by proposing local changes in such a way that this measure is invariant. And for this, the idea is that one can introduce crosses and double bars or remove them. And when we do so, what happens is that those cycles, those loops, sometimes merge, sometimes split. And if we just look at what happens on the level of the partition due to the length of loops, we get a split merge process where we take two partition elements, merge them together, or take a given partition element and split it uniformly. And so if you're in a min-field set situation, this is what happens. And then you expect that the corresponding measure should be invariant under the split merge process. And then it turns out that this is the Poisson-Dirichlet. So this was understood by Ueltschi. First, I mean, checking that this is indeed the invariant measure. And those gentlemen proved that this is, I mean, under some conditions, this is the only invariant measure. And I mean, it's still something which is not completely proved. The fact, the uniqueness of the invariant measure is proved only when this parameter theta is strictly, less or equal to 1. For theta greater than 1, there are no proofs yet. And the heuristics, in the case of this random interchange of a model with a crosses was proposed by Aldaus and actually used and proved by Schramm. It's a very nice result. And okay, the relevance for spatial models was something what we understood with Krista Goldschmidt and Peter Windrich. So now let me describe this picture. This is the visualizations of one loop in some loop model. So this is this model of spatial permutation. So from a given point, you move to another point. And so we have plenty of loops. And what happens and what is responsible for this mean field behavior is that the loops actually merge extremely well. So here you have the box. And then here you have a picture of one loop. The different colors means the different times along the loop. So you start the loop and you are like dark blue. When you move, you go to light blue, then to green, to yellow, to light red, to dark red. And what you see is that if you look at the dark blue, it's already all over. So this suggests that this the loop over here is going everywhere, then coming back and then going everywhere. I mean, the dark blue represents like the first 10% of the loop, and it's already everywhere. The yellow is everywhere. The 10% which are depicted with yellow is going back and forth everywhere. So these things mix so well that that's why they have mean field behavior. And this Poisson-Dirichlet measure, which is the invariant measure for the mean field split merge process, is relevant. So, okay.
Sorry, Daniel, can you repeat again why you call mean field the split merge process? So where is the mean field in this split merge?
Yes, so we have these partitions, and this split merge process does not refer at all to any spatial structure. So the way you run it would be to pick up two numbers at random. If they belong to different partition elements here, you merge those two together. If they happens to belong to the same, then you split this thing uniformly. So you go from one partition to another, and there is no reference to spatial nature. And then it turns out that Poisson-Dirichlet is the invariant measure here. And I mean, I've been going a bit fast, but then the idea is you do the same thing for this measure, which has the spatial structure, by introducing a suitable split merge process. I mean, so you change the crosses and the double bars, which amounts to changing these loops. It's clearly a split merge process in the sense that you get the partitions with the lengths of the loops and you go from one to another. But what you would expect is that the rate at which you select 2 points is heavily dependent on the space and perhaps the past. So you expect a lot of correlations. But no. So the observation is that in dimensions 3 and higher, for very large systems, this behaves effectively like mean field. And the picture is that these things are mixing so well, that if you have two loops, they interact in all sorts of ways. The probability that you are going to merge them only depends on the respective lengths of these loops and not on the rest. I mean, somehow the time under which you do the changes depends on the microscopic things, but it's only a rescaling of the time. So the limiting measure does not depend on the microscopics of the thing. So this is the intuition. I wanted to explain a little bit mean field systems. That's something that I did with Jakob recently. So in something which is not hard to check is that if you look at this kind of expectations in the quantum system, this gives rise to this kind of expectation in the corresponding loop model. So we have this product over all loops of the Koch involving the length of the loop. And then what one expects is that so one would expect that for a large system, this behaves, I mean, that's this, but this is Poisson-Dirichlet. One can calculate this and one gets this kind of function. And in some cases for mean field systems, one can actually calculate it. So this is something quite interesting because this can be sometimes calculated on the complete graph. And we get this function over here. And this is indeed a function which is compatible with the corresponding Poisson-Dirichlet. The question is whether this actually characterizes the Poisson-Dirichlet distribution. And that's an open question, but we have some results with Jakob, Peter Mertens, and Cécile Maillet, but we are far from fully understanding it. So anyway, for the complete graph, we can prove this kind of things, that this expectation with these loop models converges to this thing. If u equals 1, we are in the Heisenberg regime. Another function if we are in the XY regime. And this is compatible with Poisson-Dirichlet, but it's not enough to conclude that it must be Poisson-Dirichlet. I wanted to discuss so actually, right, I'm going to re-outline. So there is a model which is associated to the ideal Bose gas for which things can be done quite explicitly. And one can indeed prove that it's Poisson-Dirichlet. So it's kind of nice because it is a spatial model, but when you look at the things, we are really averaging in such a way that the spatial nature completely disappears. And then it becomes something about uniform permutations, which is not too hard to check. If you take uniform permutations and the joint distributions for the length of cycles, it's Poisson-Dirichlet of parameter 1. For classical spin systems, we have also some kind of loop models. And so the picture would be here. So we have a domain. I mean, we have to imagine it in 3 dimensions. We can look at different points. We have a probability distributions on suitable loops. And we can also ask, I mean, the length of the loops. So something that we could somehow do rigorously. The statement is a bit ugly, but in essence, it's this. Suppose we have several points over here. So each points belong to some loops. Some will belong to the same loops and some to different loops. So given a couple of points, like, okay, here only 2, but it's more interesting when there are at least 4, we can look at the corresponding partitions of these 4 points according to the loops. So we put together those points in the same loop. And we can look at the event that all those points, I mean, when they are partitions because of a loop, form an even partition, which means that all those groups have even numbers. And then we can prove rigorously that the probability for even partitions is the same as the probability with Poisson-Dirichlet of even partitions. So I don't have too much time to explain it. It's something that I did with Costanza Benassi. And the trick here is that we used properties for the classical XY model, namely that it's known that the Gibbs states are represents a magnetization in some directions and uniformly in some, which can be anything in the XY plane. And using these things, one can actually calculate this thing and see that it's compatible with the corresponding thing with Poisson-Dirichlet. So this is, it's a bit complicated and I'm doing it very fast, but this is a result for loop models in dimensions 3 and higher, but in with genuine spatial structure. And it goes a little bit beyond saying just that there are infinite loops, but some correlations are given by the Poisson-Dirichlet correlations. It's not enough to prove Poisson-Dirichlet either, but it's already more. I mean, if somebody says it's Poisson-Dirichlet of parameter 1, somebody says it's Poisson-Dirichlet of parameter 2, then this will not have the same probability for even correlations. So you can definitely dismiss some distributions. So let me conclude. So I introduced loop representations for quantum spins. There are also loop representations for classical spin systems. It's also probability of loops, which are one-dimensional objects living in three-dimensional space. And all these things should have universal behavior. The the joint distributions of the length of the loops is always Poisson-Dirichlet of various parameters depending on various situations. Some proofs for the complete graph, the ideal Bose-Gas, and some very partial results, which I outlined very quickly for this for the model which corresponds to the classical XY model. Sorry for having rushed at the end. Thank you for your patience.
Thanks a lot, Daniel, for these very interesting talks. Are there any questions on site or online? There is one, maybe. Okay.
So,
no.
Dimitris,
Yes. You should. Yeah.
Thank you very much, Daniel. About universality, so I was a little bit, it was not very clear to me because you showed many models, many behaviors. So what is exactly that is universal?
So,
Because, you know, there are the dimensions, the type of graphs, the parameters, so is, do you understand a little bit which part of it is behaving in a universal way, or?
yes, so what is universal is that this part of partition should be one Poisson-Dirichlet. All models of when you have these one-dimensional loops living in three-dimensional space, say. Yes, or higher. So in 2 dimensions, you would expect, I mean, it's a bit related to the fact that random walks would actually be recurrent. So you would probably not get this infinite, I mean, these macroscopic loops. But when you have macroscopic loops, then you have this behavior. Yes. So of course, in these systems, I mean, we have this beta. If beta is small, you have only a microscopic loop. So it's kind of compatible, but in a totally trivial way. But as soon as you have microscopic things appearing, it's going to be a Poisson-Dirichlet. And the parameter turns out to be related to the symmetries of the system. But here, I don't have a theory. It's more like observations in different models. Actually, it's not even this, because if you look at classical XY versus, or classical Heisenberg versus quantum Heisenberg, for quantum Heisenberg, it's Poisson-Dirichlet of parameter 2. For classical Heisenberg, it's Poisson-Dirichlet 3/2. I'm not quite sure how to understand that. So that's the part which is universal.
Yes.
So I was wondering about the graph with 2 peaks. What sort of object do you measure to get the 2 peaks in the simulation?
The peaks here?
Yep.
So I just mentioned this nematic order parameter. So this is a model of spin 1 systems, and we look at the, I mean, what would correspond to the magnetization, which would be like what are the volumes, sum of these spin operators, but we take actually the spin operator to the square. So that's this. So you sum the Sx, the spin operator at site X. I mean, you fix a component and you square this, and you average this.
Okay, thanks.
I was curious about the ideal Bose-Gas, sorry. In particular, do you expect the same result also be true for some interacting
Yes.
one in general, or only mean field, like, or more generally?
In general. So if you take this Feynman-Katz representation, so you have all these Brownian trajectories with interactions, yes, you expect it's Poisson-Dirichlet 1. Now, I'm not sure about, I mean, I cannot tell you any practical consequence of this. But yes, I mean, you can introduce a probability model with these Brownian bridges. One expects a transition to infinite loops, and yes, it would have Poisson-Dirichlet 1.
Yes, you anticipated my second question. That was precisely on the physical ground if one could measure that for Bose-Gas, some distribution related to some measurement that one can perform.
No, at least not in this Feynman-Katz representation. I mean, here for the quantum spins, it's related to this symmetry breaking and the nature of phases. One can do calculations both assuming that the system breaks the symmetry in some way and get some expression, and in such a way that one can also do the calculation with Poisson-Dirichlet and match them. So for instance, for the hardcore Bose gas, which is equivalent to the quantum XY, one could do something like that and prove indirectly that we get this U1 symmetry breaking. But for this trajectory is due to this Feynman-Katz picture directly. So definitely our Poisson-Dirichlet one, but I don't know what to do with that. That's a good embarrassing question. Yeah.
Would be interesting. So I don't see any other question.
We have one question online.
Thank you, Anastasia.
Diego,
Hi, Diego.
we cannot hear you yet.
Can you hear me?
Yes. Yes.
Okay. Okay. Thank you for the very interesting talk. I wanted just a curiosity. Is it possible to use this loop representation for spin glass models? Is there anything known or tried about that?
So this is a good question. I would say yes. Now, what to do with them, I don't know. But you could imagine some spin glass. For instance, if you have, I mean, we have these interactions with Heisenberg ferromagnetic or anti-ferromagnetic. So now if you had like a spin glass with random interactions, I mean, yes, ferromagnetic or anti-ferromagnetic, this would correspond to situations where in some edges you would have crosses, in the others double bars. So yes, you can represent the partition function, you can represent the spin correlations. Now, what to do with that, I don't know. But in principle, okay, yes, yeah.
Okay,
yeah.
Thank you very much.
So I think now it's the moment we can say thank you for this very nice talk once again, Daniel. And again, Daniel is here in those days, so if you have further questions, you find him at the new building, first floor, and you can discuss. It will be a pleasure. Thanks once again, every one of you, for being present to the Colloquium talk.